Hi all, Dr. Clark here again, and today we're going to talk in natural resources about nuclear issues. So we left off talking about nuclear energy and nuclear power last time, and I was talking about how um, nuclear power comes about. So the breaking of atoms, especially uranium, okay, and plutonium, the breaking of those isotopes to release neutrons, have the neutrons start what we call a nuclear chain reaction, which releases a bunch of energy. That energy is captured by water, vaporizes the water, which then spins a turbine, and through the turbine and magnets creates electricity. Um, Today we're going to talk about issues with nuclear power that we've seen in the past, and you can kind of be the judge of whether or not nuclear power is worth exploring, um, or if we should abandon nuclear power and move to some other resource. Okay, so what happens when we want to get rid of a nuclear plant? Okay, so we're going to examine that. Nuclear plants last about 40 or 50 years. Same thing with most power plants. Fossil fuel power plants last about 40 or 50 years, and then they need to be decommissioned. They need to be destroyed. Now, there are a couple ways at which nuclear are destroyed, and we'll talk about those in a little bit. But it's a serious issue when you're going to remove material that could be radioactive, okay? And then leave that, at least some of that material, that radioactivity, on the landscape for future generations. All right, so let's jump into it. So these are issues that are related to the use of nuclear as fuel. Okay? Most of it has nothing to do with the actual process by which we get energy. Okay? Yes, of course, the individuals, the workers, could be exposed to the radiation. That's a concern. But the main concern is those nuclear fuel cells or fuel rods that last about 3 years. What do you do with them when they're done? How do you dispose of them? How do you dispose of any waste? Now, nuclear fuel, like pretty much all the other fuel types, fossil fuel and things like that, when you're talking about a power plant, you're talking about lots of water and the use of water to vaporize that water, spin turbines, create electricity. It doesn't matter if you're running it on nuclear, if you're running it on coal, if you're running on oil, if you're running it on natural gas. Those power plants pretty much all work the exact same way. Vaporize water, take that steam, spin a turbine, create electricity, okay, and now you have power in the power grid. Okay? So part of the aspect of issues would be, how are people protected? The workers, okay, and the nearby um, public. Okay, so individuals that are within a certain distance from the nuclear power plant. Okay? And we often look at this. We often look at the effect or the issues based on some kind of absorptive dosage. Okay? So how much radiation or how much of this energy is absorbed in the tissue, absorbed in the concrete, absorbed in the waterways, the soils. Okay, what's around. Okay, and you guys have probably heard of like Geiger counters and things like that. They're really measuring that leftover energy. Okay? And so we can measure this in what we call grays or rads, and we can get a idea of what's the exposure level. Okay? Like I said before, there are three types of energies, or types of energy that comes from nuclear fuels. You have alpha particles, okay, which I said you can be protected from just the skin layer. You have beta particles, which you need kind of clothing protection for those. And then you have gamma, which just flow right through you. And there's really no source of protection from gamma. I mean, we make our nuclear power plants to try to hold in the gamma, and that's why they're giant concrete, really thick concrete walls, reinforced steel and everything like that. But still, nonetheless, the gamma particles can move through a lot of that. Gamma rays can move through a lot of that. So when we look at the danger of nuclear, okay, it really comes from the alpha particles. Okay? They're about 20 times more dangerous or damage causing. And when we're talking damage to DNA. Okay, we're talking damage to your genetic code, causing mutations, causing things like dimers. And dimers are when one side of your DNA binds to itself. So you can have what we call a thymine dimer, where thymine is occurring on the same side of your DNA and it just sticks together. You can have a guanine, cytosine, adenine dimers, okay, and they just stick together. This causes a mutation, so that when the DNA is copied, it looks like you only need one nitrogenous base to pair up with that dimer. So this causes a point mutation and often a frameshift mutation and can really destroy an individual's DNA. Okay, now depending on the dosage, okay, so you also have a factor that you have to include is dosage time, okay, or the amount of time you've been exposed to a certain dosage. So both are taken into account. Okay? In some cases, if you're just exposed once, okay, to a high dosage, that's enough to destroy your DNA. And other times, if you're exposed to just small amounts of radiation or small amount of rads over a long period of time, that's enough to cause mutations. So it's really not just the dosage, but also the equivalence or how long you've been exposed to that certain dosage. Okay. Now, like I said before, when you're affected with, or when you've been subjected to alpha or beta or even gamma radiation, okay, what's going on is it will interact with other atoms in your body and it will create ions. So it causes other atoms to lose or gain electrons. Okay, so it depends on the atom it's affecting, but it causes them to form ions, the loss or gaining of electrons. So we call this ionizing radiation. Well, when you lose or gain electrons, it changes the binding forces within parts of your body, mainly your DNA. So if your phosphate's backbone of your DNA is going from being negative charged to positively charged, okay, it's going to cause that DNA to bind differently. It's going to cause other things to bind to it, which is going to mess the DNA strand up. Okay, so it causes mutations. So we know that radiation causes mutations, not just radiation from nuclear power plants in the form of alpha, beta, and gamma, but we know that radiation from just the sun, solar radiation, UV radiation, can cause mutations. Okay. Now, the issue often is, where do these mutations occur at? Are these mutations occurring in somatic cells? And when we say somatic cells, we mean tissue that is not reproductive. Okay. If it occurs in somatic cells, non-reproductive tissue, it can cause the individual to develop cancer. Okay? And sometimes all that means is that you've just mutated things like your p53 protein, which is a protein that checks DNA for mutations. So if you mutate or change your proofreading system, then it doesn't proofread right, and then mutations can be passed on and through the cell cycle. It's kind of like using a Word document. So you write a paper, and then you spell check, but instead of having spell check in English, so let's say you wrote the paper in English, you change the spell check to Spanish. Okay? And so now either everything's right or everything's wrong. And that's exactly kind of how your DNA proofreading system works. If you mutate your proofreading system, which is often what happens, okay, then all mistakes can be passed on, or all pieces of DNA are terminated, okay, which can cause some major issues in the organism in question. If the mutation occurs in the germline cells, okay, so not the somatic cells, but in the germline cells, so it occurs in cells that are going to make sperm or egg, then you can pass that on to the next generation. These are real concerns because you can be passing on a mutation to your offspring. Okay? And so you can have both cases from ionizing radiation. You can have both cases happen. You can have DNA that's mutated in somatic cells and DNA that's mutated in germline cells. Okay? So what do we use? We use protective equipment, at least for workers. So we use radiation suits, okay, like this. We use Geiger counters, okay, to see, what the, how many rads are in certain areas, etc. And these all this equipment has a certain half-life. So you can only wear the protective equipment for so long. It can never go home with you, these kind of things. And there's issues with this, and we can talk about those issues from the mining standpoint, because people who mine uranium will often, they might wear some protective coating, but they're going home with their boots. Okay? And we still today can go into regions that you had uranium mines next to small towns, and you can go into people's houses where their significant other worked in the uranium mine, and you can still get a Geiger counter to read radiation in their house, which means that they're wearing radiation home. They're bringing it home. They're wearing their boots in their house, or kicking their boots off at the door, but there's enough radiation that it's still counting. It's still registering in these old abandoned houses. There's many places all over the United States, which we call ghost towns, around places like uranium mines, that you can look and you can still see radioactivity in people's houses that have been abandoned for 20, 30, 50 years. And it's a result of these practices that weren't very good at the time. They're getting better for sure, because we know a lot more about the mutations that it can cause and the half-life and how long it can stay around. But nonetheless, we still have issues. Okay, so all this protective equipment has a certain time period at which you have to wear it, and then you have to dispose of it. Okay, and there's issues with disposing of the protective equipment also. So let's look at radiation effects. Okay? If we're talking about something like a plutonium explosion or a nuclear bomb blast, okay, or an accidental exposure at a nuclear facility, like the nuclear facility erupts, burns, etc. Okay, we're talking about a dosage of about 100,000 REMs, okay, and it will cause immediate death. Okay? A nuclear accident or accidental exposure to X-rays, okay, it depends on how often or how much you've been exposed to. Okay, 10,000 rems, okay, death in about 2 days. 1,000, death in about 2 weeks. 800, you're going to die eventually. Okay, 500, you got about 50% survival. So there are lots of situations where, um, you know, exposure to any nuclear material can cause pretty high death rates. Okay? And then even less, 100 rems, you have, an increased probability of developing leukemia, which in many cases is a death sentence in its own. Okay? 50 rems, you can change the number of blood cells that you have. 10 rems, you can change embryos, so have abnormal embryos, and even just like an X-ray of, say, like your intestine, okay? 1 rem, okay, we have seen damage. We've seen damage to cells, um, and it depends on the individual on what kind of effect that individual will have. So there's lots and lots of situations where we don't know. We know, like, on average, and we know like 100,000 rems is going to cause immediate death. But, some of these other situations, maybe 100 rems is enough to cause, death in that individual. And, and this goes to just show you it's the same thing as cancer. 1 in every 3 people or so will develop cancer in their lifetime, 33% chance. Exposure to radiation greatly increases the chance. So now instead of maybe 33% chance, now maybe you got a 50-50 chance. Okay? If you're exposed to even more radiation, like you work in a nuclear plant, maybe that increases it to even 60 or 70% chance. Okay? And so nonetheless, radiation can increase your effects of mutations and cancer on the human body. Okay, so how safe is it? Well, depends on a couple things. So maybe you've heard of the 3 Mile Island nuclear plant. So there was a partial core meltdown in 1979. Okay. Now, again, like I said, the safety really depends on a couple things. It depends on, first of all, the equipment used, but secondly, it depends on the individuals in charge. So sometimes you'll get meltdowns, you'll get problems that occur because the equipment is failing, but all reactors, all nuclear power plants, okay, have safety valves, and they have ways at which you can contain the issue. Sometimes the reason why we have problems is because operators don't know what to do if there is a malfunction. Right? So individuals might be not trained very well, or they might forget all their training when all the whistles and all the bells and all the red lights are on. They might forget what to do and make errors. Okay? And that's exactly what happened with 3 Mile Island area. The operator in charge just compounded the problem by causing a malfunction in the valves. All right? Now, like I said before, there are safety procedures. Okay, so you get containment, and containment happened. However, the containment normally just contains the material so it's not pouring out into the river or pouring out into the lake. So remember, nuclear power plants are going to occur next to water. They have to occur next to water. They utilize a lot of water. And so almost all nuclear power plants occur next to water. Okay? And so the containment structures, and this is a great thing, they're designed to prevent nuclear waste from going into waterways. Okay? which is a really good thing. However, often they don't have another mechanism to prevent nuclear waste from being evaporated or vented off into the atmosphere. Okay, and that's exactly what happened with the 3 Mile Island. It was contained so it doesn't pour into the bay or into the rivers, but it was not contained from the atmosphere, and nuclear waste was spilled into the atmosphere. Now, what happens when one of these fail? Right? You got to spend a lot of money. Right? That reactor was shut down in 1990, and it cost about $1 billion to shut it down. And then on top of it, you have to wait, because normally you're not just dealing with a single reactor on the landscape. Maybe you have a bunch of reactors in chain next to each other, because if you're going to build a nuclear power plant and you get the rights and the regulations to put one somewhere, you're going to build the biggest facility possible, because they're very controversial. No one wants a nuclear power plant in their backyard, right? And so when you get one and you get the rights to put one there, and then typically they're built to last, or at least built in large quantity. Okay? So now one fails, you have to wait until all the rest of them are decommissioned. So until all the rest of them have met their 50-year quota or 40-year quota, depending on the plant type. Okay? And then you can shut them all down and remove it all at one time. So that's exactly what we're doing with the 3 Mile Island nuclear plant. The one that was crippled has already been shut down at $1 billion. And now we're waiting for the other reactors nearby, and I'll show you a picture of this, okay, to end their useful life period, and then we'll remove all of it. So here is 3 Mile Island. Okay? You can see these steam stacks are not functioning. That's because they've been shut down. Okay? And so this is where the reactor malfunctioned. So you can assume, and maybe it's bad to assume, but there's waterways on both sides of this. It's an island. It truly is an island. Okay? And that is a concern to a lot of citizens downriver, is what happens if, one of these flood? What happens if nuclear waste gets into the waterway? Most of the water downstream, most of the drinking water is going to be coming from rivers. And now you have these nuclear waste, nuclear products coming into the water. Okay? This will be a concern when these are shut down and this entire island is removed. The material is removed off this island. What happens, if you get a truck spilling some nuclear waste soil into the water? What happens if pieces of this, dust or something like that that's coming off of the construction settles in the water? Is it going to hold enough radioactive material to poison the water? It's a concern. Let's look at another one. Chernobyl. Okay, Ukraine. You probably heard of this one also. Okay, it's the world's largest nuclear accident occurred in 1986. Okay, and this again was the fault of human error. So most of the reactor issues that we have are the result of human error. Okay? Now, again, we have 450 reactors, and there's only been issues with a few. Okay? Well, large issues with a few, large exposure with a few. Okay? So at the time, they were conducting research to try to make the reactor better. So they shut down a lot of the safety apparatuses to try to enhance the reactor's capabilities. Well, when you shut down all the warning systems, they actually had a issue, in which that the cooling system of the reactor was shut down. So you couldn't cool the core, and it overheated. And when I say overheated, okay, it took 4.5 seconds for the energy level of the reactor to increase 2,000 times. Okay? This is how quick things can change in a nuclear power plant. And so what happened was, when they finally got the system, try to get the core of the reactor to cool down, it converted all the cooling water into steam, and it blew the concrete roof off of the reactor. The reactor then caught fire, and it took a long time, 10 days, to bring the reactor under control. So for 10 days, the reactor is on fire, roughly 10 days. And fire means smoke. Smoke means that some of this, radioactive material is getting into the atmosphere. But on top of it, you have dust, you have material, you have winds that are taking material different places, because you have a fairly large explosion that occurred at this nuclear power plant. Okay, it resulted in 37 deaths, and about 500 people were hospitalized. Now, remember, this is occurring in Ukraine, so some of the information might not have been projected quite as honestly as you would expect. Okay? And so a lot of the people that were evacuated, we assume, were also affected by radiation, because after we see the people that were evacuated, we start to see things like high increases in the frequency of thyroid cancer, and that's the result of iodine, radioactive iodine, being released. Okay? You can see the exact same thing, these thyroid cancer issues, if you know anyone who lived in Death Valley or other places where we tested nuclear bombs. So when we were testing to see if nuclear bombs work, during World War II, but also into the Cold War, we were still doing tests to see if nuclear weapons and to work, and we chose places like Death Valley, out in the middle of nowhere. But what happened is Death Valley has communities nearby, so you'd have these explosions go off, these big nuclear weapons explode in the desert, but you'd have the dust, the radioactive dust, settle in these environments where people lived. Okay? And kids and things like that would be playing on the playground, and there'd be a little layer of nuclear dust, okay, on the swings and slides and things like that, and the kids used to just wipe it off, or there'd be some on the car and they'd write their names in it and things like that. And there's been massive number of kids that grew up in those regions that now have thyroid cancer. Okay? And it's really the result of these nuclear tests. So the same thing happens when a reactor blows up, okay, or a reactor has a fire. That dust, that material, can travel a long ways and carry radiation with it, okay, which can cause serious problems in individuals later on in life. Okay, so here you can see the accident in Chernobyl. Okay, you can see the explosion of the reactor. You can see there what that looks like. It's still functioning. Chernobyl is still working. Well, not this piece, but the reactor is still working in places. Okay. And then the one that's probably most near and dear to some of you, because you probably heard about it recently, 2011, there was a magnitude 9 earthquake, okay, in Fukushima, and that caused a tsunami. And the tsunami hit the nuclear plant, as you would assume, given that nuclear plants are near waterways, including the ocean, and we had some major issues going on. You had the heat exchangers were damaged, and the emergency power system was flooded, and so the operation was stopped, but you had leaking of the cooling system into the seawater. So how much radioactive material was left in the cooling system, we don't really know, but we assume that there was quite a bit of radiation that could have leaked into the ocean, right? And also into the atmosphere because there was fires and explosions. But again, these are just pieces of the reactor safety that are a concern. Now, three major problems in, say, 60, 70 years, it's not horrible. There's been a lot more mine collapses in that amount of time, but there are a lot more mines. There have been a lot more natural gas wellheads explode in that amount of time, but again, there's a lot more natural gas wellheads. So you have to take this into account that, yes, there's only been a few reactors go down and explode, but nonetheless, the safety and the long-term effects of radiation poisoning might be much greater than, say, an explosion at a wellhead. So what do? Let's say these power plants are at the end of their life expectancy. Okay, most have a 30 to 40 to 50 year life expectancy. Okay? And like I said before, this doesn't matter if we're talking fossil fuels or nuclear. It's about the same thing. Okay? Now, when a fossil fuel plant reaches its end of its life expectancy, we just tear it down. We just destroy it. You can build a new one right in the same place, or you just go a little bit over and build a new one. Okay? But when a nuclear power plant reaches the end of its lifetime, okay, it's decommissioned. Okay? And there are three main ways at which this can occur. So you can decommission it by removing and disposing of all the fuel rods, okay, and all the water that was used in the reactor. Okay? So big giant vats of water, fuel rods, etc. are removed from site. Okay? Then stage two, you can disposition or destroy the facility. Now there's a couple ways at which this can occur. You can allow the facility to sit on the landscape until the half-life of some of those intermediate radioactive molecules have been spent. Something like the iodines and things like that. Once those have all been degraded over a certain period of time, then you can demolish the facility. In other cases, okay, depends on the country also, clearly, you just demolish the whole thing, but all the material from the demolishing, okay, is buried. Okay? And so we're going to watch a little video about what the United States does when we try to either decommission, okay, or dispose of nuclear waste.
Trace, it's your turn to take out the nuclear waste.
Oh man, I don't even know where to put it. Hey there friends, welcome to D News and thanks for tuning in. I'm Trace. Nuclear energy is controversial to say the least. Those who are for it say that it can provide relatively cheap, safe, and clean energy. Those against it point to expensive plants and fuel, plus the storage of the spent waste. Then when accidents do happen, they're visible, devastating, and deadly. So nuclear's got a lot going on. Regardless of whether you're for or against it, everyone can agree nuclear waste is a troubling issue. Recently, at the Waste Isolation Pilot Plant, or WIPP, in New Mexico, a radiation alarm went off. Someone screwed up. 15 years ago, WIPP became the first and only permanent geologic nuclear waste storage facility in the country. But now, The Verge is reporting substandard kitty litter might bring the whole place down. Back in February, part of the place had to be shut down, the air vents were permanently blocked with high-density expanding foam, and people were evacuated. The problem was kitty litter. Someone packed nuclear material in organic kitty litter, which is made of wheat or corn, rather than the inorganic type that they almost always use. That tiny change caused one of the waste barrels to burst, releasing radiation and setting off alarms. I didn't realize they packed nuclear waste in kitty litter. That's pretty weird. When you hear nuclear waste, you probably picture a soupy, glowing green liquid like you see in The Simpsons or Futurama. In real life, nuclear waste can be any number of things, from tools and parts from nuclear plants to spent uranium fuel rods or pellets. Seriously, after too many wearings, even the uniforms they wear in the plant are put into nuclear waste barrels. According to the Department of Energy, the United States has 75,000 metric tons of spent nuclear fuel. The waste is stored at 122 temporary sites in 39 different states, but only WIPP is, and maybe was, the only permanent site in history. So since we're obviously not throwing it at the sun, what the heck are we doing with this stuff? Well, there are ways to reprocess the radioactive spent fuel rods to remove plutonium for use in warheads, but due to fears about nuclear weapons proliferation, nobody really wants to do this. Another thing is to burn the waste in fast neutron or traveling wave nuclear reactors. They're different kinds of plants that create energy from the remaining atoms and further reduces the final waste product. But there's still that kicker. There's a lot of nuclear waste still at the end of the line. No matter what we do, our best option right now is called deep geological disposal. Basically, we're burying it. Though even how to do that is debated. At the moment, WIPP is the best plan, but others include drilling almost 2 miles into the earth and leaving the stuff down there forever. And there's also an option to put it into shale or salt mines. WIPP is a dry salt bed, after all. They dig down like a mine, and then they dig out areas that they can keep those barrels of nuclear material in for the next tens of thousands of years. So which do scientists prefer? They don't know. They're not actually sure. Most are concerned with groundwater contamination, earthquakes, cave-ins, and other problems with underground excavation. At the moment, there are a few places where the conditions are just right, and they're not concerned about these things. But considering we've got 104 nuclear reactors generating waste in the US alone, the problem is mounting. So what would you do with nuclear waste? Contaminate the comments with your thoughts and subscribe for more D News every day.
Okay, so there you can see what we deal with, or how we deal with nuclear waste in the United States. Like I said before, our fuel cells are not reused. Okay, we could reuse our fuel cells, which would cut down on the amount of waste. It is kind of a tedious process and it's expensive. So when we're talking about nuclear power, when we're talking about power in general, when we're talking about energy in general, most companies, most regions that want energy, they want it as cheap as possible, okay? And they want it as fast as possible. And now, more recently, they want it as clean as possible. Okay? And so by doing that, we still have not, nuclear power is very clean. Okay? Except for the end product is very, very nasty and concerning. So right now we have not started to recycle our fuel rods. We could, and that would reduce the waste, but we're still going to have waste. Okay? And so there's a lot of controversy around where we're going to put the waste. There have been probably another 5 to 10 sites located that over the past 10 years or so have been documented to be good sites for permanent storage of nuclear waste, much like the one in New Mexico. There are 3 that have been demonstrated in Arizona. Now the issue with some of these sites is that the government doesn't own the land. So 2 of the sites in Arizona are owned by Native Americans. Okay? They're part of the reservation. It just happens to be that that land has very little water very little chance of earthquakes, etc. And so they're thinking about putting it under these mountain ranges, so digging down really deep mines and storing it under there, and then collapsing the mine and sealing it off, so no one ever goes in there. And that's ways to get rid of nuclear waste permanently, supposedly. So the problem with a lot of these issues is what happens in future generations. What happens when future generations are exploring for new minerals or exploring for new sources of energy? Right? How are you going to mark? How are you going to demonstrate that that region should not be explored? Okay? This is difficult and very concerning. Okay? But nuclear power still exists. More plants are being constructed every year, and it's just part of the problem, part of the issue that we're going forward with is what do we do with the waste afterwards? Okay? And there are proposals to send it to the sun. Okay? I'm not entirely sure if that's a good idea or even cost effective. Remember, most of the waste disposal, the reason why digging a mine and sticking it underground is utilized is because it's actually relatively cheap compared to some of the other methods to dispose of waste. Okay? With that, we're going to move from non-renewable resources to talk about renewable resources in the next few lectures. Okay?